Much, Benjamin, to come and talk about your work in this series of seminar. So today you're going to talk about the machine learning application for to cosmology and large surveys. And as you mentioned in your abstract, there will be 2 other talks by your collaborators or previous students in the coming weeks. So thank you very much, and I'll leave you the floor.
Thank you, Philippe. So first of all, let me acknowledge the fact that this work, of course, would not have been possible without a large number of collaborators, which I will highlight throughout the talk. And has been the work has been going on here at IAP and in collaboration with our international partners. Recently, we were funded very recently. We just started the project a couple of months ago. We were funded by the Simons Foundation as part of a new Simons collaboration called Learning the Universe. There's a link here at the bottom. Can you see my cursor when I move it? Or is it very small? Here is a link at the bottom that gives you some more information about that. And really the collaboration is addresses many of the problems that I mentioned today, with the goal of constructing a new way of interpreting cosmological data sets, both from theoretical modeling all the way through computational prediction, and using some of the techniques that I'll be mentioning today, to do the analysis and learn from cosmological data sets about underlying cosmological problems. So let me keep going. Here we go. So I know that some of you are not cosmologists. So let me just show you on one slide what cosmology is all about. Essentially, it's about our past light cone. That's just all that you see right now. When you look into the sky, photons that started a long time ago reach you today. Photons that started not so long ago reach you today. And they all reach us at the same time. And so we get a view of the universe at different distances and different times. And these various observables that we use cosmologically are listed here on the left. Most of those we've actually already observed, some only indirectly, and some we're still waiting to detect, such as primordial gravitational waves. And on the right, you see a timeline of the history of the universe as we understand it, with some process in the early universe producing a large, smooth initial state for the universe with small perturbations in a radiation-dominated era. So the Big Bang is typically the beginning of this radiation-dominated era, but there was a time before that era where the universe, where these fluctuations were created, and the universe got into that initial conditions state. Typically, people think of that as inflation. The elements were created. At some point, the universe stopped being dominated by the radiation, became matter-dominated, but still very hot. At some point, it became cool enough that protons started capturing electrons and making hydrogen atoms. That epoch is called recombination. And at that point, the photons started decoupling from these electrons because they were now bound up in neutral atoms mostly, and started free streaming throughout the universe. So this is really up to here is where we see the light cone. Beyond that, we don't really see photons coming from the light cone because photons here still scatter a lot. But at this point, basically, we see objects. Photons travel more or less on straight lines up to lensing effects, which are also interesting as a way to probe the dark matter distribution. But they travel on geodesics, which is what defines our past light cone. structure starts eventually lighting up. So we start seeing stars and early galaxies. That light starts reionizing the universe into the state that we see it today, where most of the universe's volume is ionized. And then very recently in the cosmic history, we notice that the expansion of the universe starts accelerating again. So if inflation prepared the universe essentially at very early times, that was an epoch of accelerated expansion. Now it starts accelerating again. And we typically talk about that in terms of dark energy as a way to start this acceleration. What do cosmologists want to learn from all of these observations? We want to learn about the cosmic beginning. I mentioned one model is called inflation, one class of models. There are parameters that describe that. We want to learn about the content of the universe, and we want to learn about the fate of the universe. So how will the universe, what will happen in the future? And that's going to be strongly dependent on our understanding of dark energy. So here are some physics aspects that are related to those. So what are the initial conditions? How did the perturbations in these initial conditions grow into the structure that we observe today, the large-scale structure of the universe that we observe in the cosmic microwave background and in large-scale structure observations today. We want to understand the dynamics and measure the dynamics of the universe. How do things move around? That gives us a lot of information about the content of the universe. And we want to understand how the universe expands today. That's the most promising way of determining the nature of dark energy. These parameters here have to do with a lot of things that various astrophysicists are interested in. And as cosmologists, we're trying to constrain all of those parameters. So initially, for example, in an inflation, you have these parameters describing the initial conditions. R refers to primordial gravitational waves that will be created during an epoch of inflation. In most models of inflation, there's a very, very small amount of non-Gaussianity. In fact, there's always a very small amount of non-Gaussianity. Some models it's larger, so we want to learn about that. This refers to dark matter, baryons, the baryon content. A lot of these observables are somewhat sensitive to the neutrino mass, so that's still an undetermined quantity from particle physics. Dark matter, of course, is a cosmologically, astronomically motivated bit of particle physics that is not in the standard model. So very strong evidence for beyond standard model particle physics from that. And then tau, for example, is parameterizes the reionization history, which has to do with early star formation, the formation of the earliest galaxies, black holes. So that touches on many topics that people are interested in, various bits of astronomy and particle physics. And of course, there's the H0 tension right now, where we try to understand whether cosmological models are in agreement with local determinations of the expansion speed of the universe. Okay, so in this past light cone that I showed you here, it's up on the top right, the base of it, this disk at the bottom, is really a 3D ball. I had to compress the 4-dimensional structure of the universe into a 3D drawing onto a 2D slide. So this disk here is actually a 3D ball, and the perturbations here, the metric perturbations on this in this ball, determine everything that happens afterwards. So and what the cosmological inference problem is a stochastic problem. It's a probabilistic problem because these perturbations here are random, and some process we understand that to be most likely quantum fluctuations that laid down these random fluctuations here initially. They determine everything that happens afterwards. that's something we're particularly interested in because we want to learn about what happened in the beginning of the universe, how come our universe started, and how, and what can we learn about fundamental physics from that. And so this three-dimensional ball of initial conditions is also of very strong interest, and it can teach us about the particle physics that was responsible for creating the universe in the beginning. Okay, so as physicists, we start from initial conditions and we predict forward. So we take some assumptions about these initial conditions and their statistics, and we now have, using all of physics, essentially, we can predict what the observed universe will look like. I've already told you what all these observations are. Here, put some pictures just to remind you. And these initial conditions here, as I said, they're parameterized by some numbers. The forward model is also parameterized by these other parameters here about the cosmic content, dark energy, dark matter, and that if we have powerful enough computers and good enough theory, then in principle we can predict everything that we see in data. Now the inference problem just turns this arrow around, like you just saw. Okay, so the inference problem says, let's go out and measure these, and then we want to learn about the initial conditions and all of these parameters that I talked about. So that's all it is. It's just turn that arrow around. Unfortunately, it's a big inversion, and a really like the mother of all inverse problems. But we have a lot of physics and structure to guide us. So that's why it is even remotely possible to do this. So this was all about the cosmology and about the problem that we want to solve. But the title was Machine Learning in Cosmology and Beyond. So what is the machine learning used for here? Why are we interested in using machine learning? Machine learning is useful because this inversion needs, there's a lot of detail that goes in there, and we deal with large complex data sets. We want the information we extract about the parameters to be optimal. We want to go beyond simple approximate models in the forward direction. If you treat the universe as completely Gaussian and do everything in linear perturbation theory, then it turns out you can write down very nice closed form solutions for everything. But that's not really true even for the cosmic microwave background, where at least for the primordial signal that was still true, but the secondary signals, which are what we're most interested in now, are no longer just linear. And generally we want, machine learning is a powerful tool, and it turns out we can use it to do things that we could not otherwise do just in practice with available computational power. And like I said in the abstract, a lack of data is no longer the bottleneck for cosmological knowledge. So here's a big slide of all kinds of data sets, including some that we already have, like the Planck data, the Sloan data, CFH TLS, but several data sets that are coming online within the next few years. So Euclid, LSST, already, actually DESI has already started taking data, it's already active. WFIRST, the Hyper-Supreme Dark Energy Survey, those are already partially published. The CMB-S4 experiments, the Simons Observatory, which is an S3 level, or intermediate S3 plus for the cosmic microwave background. Those are projects that will happen in the next decade. And the interesting aspect of this is that some of these even just, for example, Euclid, LSST, and DESI, which are really happening now or within the next few years, are going to multiply the amount of information, like the amount of data we have by orders of magnitude compared to all the data that we've ever gathered about the universe. So there's a big revolution coming in terms of the data, and that should motivate us to try to actually be able to use those data in an optimal way, or somewhat optimal way at least. While it is already true that with current data, we are not limited by the amount of data, but by our ability to analyze it. Okay, I can discuss this in more detail. I don't want to spend too much time on this. Now, of course, part of the new data will also be easy to analyze. So if we just look at the very large scale data in the perturbative regime, then we will be able to get some more information out of it. But there's so much additional information in regimes where already now we have trouble doing the work. That's really also what I'm talking about. Okay, so how do we do cosmology in principle? In principle, if you're just going to a stats class, Bayesian stats class, you write down a full physical stochastic model of data given the parameters, and then you get the data, and then you have everything you need to write down this green thing here, the likelihood. You then specify the prior, so you get this thing here, and then that with using Bayes formula, you can write down the posterior here. Sorry, it's hidden by the stamp on top, but this gives you what you know about the parameters given the data. And then you just evaluate this function, search through this function, and that's it. Then that function tells you everything there is to know about the parameters. But this is not how most of cosmology has been done so far. So this is cosmology in principle, or in general, data analysis in principle. In practice, this looks different. In practice, what we do is we have some data, we pick some summaries. So a lot of cosmologists, cosmology, a major role is played by the power spectrum. So the power spectrum of density fluctuations in the universe, for example, tells you how much fluctuation is there on different scales. The bispectrum, which is the 3-point correlation version of the power spectrum, the Fourier space. Same thing on the cosmic microwave background. So the power spectrum is how much fluctuation is there on different angular scales in the sky. So we pick some of these summaries, or maybe counts of galaxies at some redshift range, or in different mass, in different bins of luminosity, for example, those are observable. So those are various observational summaries. And then we pick those summaries typically because we know how to predict them from theory. And we hope that we can extract them from the data in a way that there's not too much difference conceptually between what we get from the data and what we can predict. So we need to then predict these summaries using theory. And then we need to come up with the likelihood, and we write down the likelihood in some approximate way, typically as a Gaussian, for whatever the things are that we decide to summarize the data in. So power spectrum, for example, often write down a Gaussian likelihood for the power spectrum. So this is quite risky because, first of all, we don't know necessarily that those summaries exhaust the information content. Secondly, the theory needs to be good enough. We need to, not just for the physics, but also for the instrument, for various systematics. And thirdly, how do we know that Gaussian likelihood approximations are good enough? If you have a ton of data, sometimes that's true. In many cases, it might not be, because, and maybe some of the tensions we're seeing in cosmology, there are some mild tensions in cosmology that are probably due to these kinds of statistical approximations of calling everything a Gaussian. So let's focus on choosing summaries. All right, so can we go beyond choosing summaries? And so this first part here, I'm going to talk about a very physical form of machine learning, where the idea is, okay, let's not write down the likelihood for the power spectrum or something like that. Let's just write it down for the entire survey, the whole thing. So it's an explicit likelihood based on the field of galaxies that you see in a survey as a function of redshift. and can we then use that to infer the initial conditions and cosmological parameters? So the most sophisticated version of that exists at the moment is called Borg. It's called Bayesian origin reconstruction from galaxies. And the idea with Borg is that it incorporates all of it assimilates all the information that there is. And so using this, this is an explicit likelihood form. So that means we write down for a particular model where we say physics prior has Gaussian initial conditions. They get evolved forward under gravitational evolution. And then there are galaxies that trace down the final nonlinear distribution in some way. And then that gets observed from Earth with a telescope that only sees part of the sky, maps out part of the sky in some depth, and so forth. So all of those aspects are written explicitly in the likelihood. And then we write down, this in terms of the, like I just showed you, I mean, the posterior is a function of a lot of parameters, because the parameters include the initial conditions at all space points. So for Sloan, we're using 10 million parameters, which I'll show you examples for that in a minute. So it's a box with 10 million voxels, basically, where we search through all possible various initial conditions that could have given rise to the galaxy survey that we analyze. And then we take observations and all the metadata, galaxy catalog, we stick it into this machine, and it infers for us these initial conditions. So these are two-dimensional slices. It does that using a Markov chain, so it explores all the possible initial conditions that have support under the probability distribution implied by the likelihood that we're modeling, and the physical model, and the model of the instrument. And then because it's a physical model, we don't just get these initial condition reconstructions, but we also get full histories of the universe. Every single one is a full history that says how could these galaxies that we see in the survey have gotten where we see them, given some set of initial, for all the possible initial conditions that do that. And then we can, so here's an example of that running. Here's a slice through the Sloan data. We are sitting here and we're running these this code, and the final conditions, so redshift 0 today is what we see here, very clearly visible. You have this cosmic web structure. And where we have observations, that's very well determined. Where we don't have observations, it fluctuates a lot because we don't know, like there are all kinds of different states that are consistent with the data. And then when you look at the initial conditions, it's a little harder to see, but if you stare for a while, again, in the observed regions, we are able to reconstruct quite stably a lot of the features in the initial conditions, whereas out here, basically it fluctuates, and it could be over densities, under densities. We don't really know because we don't have observations. But this extracts all of the information in the data and tells you, for example, well, there's a few galaxies here, but clearly there is actually an overdensity here that's quite stable when you run it. So there's a cluster of galaxies sitting here. There's a wall of galaxies here. The shape is not quite sure, but it's clearly connecting these two overdensities that are very stable. And so the movie here represents the uncertainty in the reconstruction. And if you're interested in this set of techniques, this is a website that is a group of people that are interested in these and developing these further. This is a calculation. It's an old calculation. We're showing it explicitly because we were doing this already now 9 years ago, and this has of course been developed more, and this is currently the leading way of doing initial condition reconstructions in a stochastic and well-motivated statistical way from real observations. Okay, so. Because these have histories, I just wanted to show that you get a lot of extra information out of this. That, for example, you actually reconstruct all the galaxies and all their velocities at all times, and actually a distribution of velocities for every galaxy that we see in the sky based on the physical model that we have. And so this shows, for example, the radial component of the velocities, showing very nicely, here's what's called the Sloan Great Wall, a large association of superclusters. And you can see how material is flowing onto that supercluster. So there's dynamical information that we can extract from these galaxy surveys. Okay, these can then be used in other contexts. For gravitational waves, for example, we can debias H0 because we have this gravitational wave distribution. We have these velocity fields that we can reconstruct. Okay, so that's currently the most advanced explicit likelihood analysis framework for galaxy surveys. So is this it? Are we done? Can I stop talking now? No, you thought you were done after half an hour, but no. There is much more to the story, because it turns out one thing we've learned from this is that the full statistical power, even of current data, is enormous. And the key issue now is that we have to have a model that is actually good enough for the data. And if we include the information, for example, the runs I've been showing you there, is using the information down to scales that are maybe 3 times as large as a large cluster of galaxies. That's sort of the mildly nonlinear regime. Our gravity model is fine there. What we find is that the model of relating galaxies to the underlying dark matter is clearly not perfect. We still get these reconstructions out, and they give very reasonable results that we can validate with all kinds of other observations. For example, gravitational lensing observations, etc. So the dark matter distributions we get are very, very good. But if we open up the cosmological parameters, then all kinds of things happen, and we find cosmological parameters that are extremely high, extremely well constrained, but biased because the way we model the galaxies and how they relate to the underlying dark matter distribution is somewhat simplistic. So this is the key issue, is model misspecification here. All right, so we talked about how to go beyond summaries. That was the first bit that I was critiquing in the standard practice of doing cosmological data analysis. The next step is inadequate theory. Like, how do we deal with the nonlinear physics and all kinds of systematics? And that's the theme of model misspecification. So we need more reality in the data model. That's one thing I will mention. We also need to we want to have the ability to reduce the data into objects that we feel we can model well. And that's really actually the underlying thing, the wisdom in the practical way people have been doing or are doing cosmology now. The power spectrum, you can model the power spectrum and the effect of systematics on the power spectrum. People have learned to do that over the last 40 years. And so that's why they project the data set onto the power spectrum, then cut it off at some scale, and then say, this bit we can model well. So we want to do that as well, but we want to be much more flexible. So, maybe we should say that, our models work really well in many regimes, just not in the most dense regimes. So maybe we can cut and say we remove the densest areas, or we threshold them somehow. So we want to have some ways of being very flexible in cutting the data, or in projecting the data, masking the data, either in Fourier space, in real space, in density, in whatever direction, whatever projection is most useful, so that we can model whatever remains very, very accurately. And that becomes really hard with explicit likelihood methods, because the explicit likelihood becomes very complicated when you want to incorporate such projection or cutting or masking operations. And there's always going to be some residual model error, so we need to have some way of capturing that as well. Okay, so one idea this is where machine learning comes in. So here's a machine learning idea that we can marry with this explicit likelihood technique. So it's the kind of transition now towards the machine learning side. Something we call neural physical engines. They model the imperfect, or they model the relationship, the less than perfect relationship between galaxies and the underlying dark matter distribution using machine learning, a deep learning model. In fact, it's not a particularly deep learning model turns out. It turns out we can write down neural networks that have very specific structure that encodes and very specific constraints on, for example, the kernels of the neural networks that encode relevant physical symmetries or constraints, so such as translation invariance, that's a convolutional network, local rotational invariance, so that means we enforce that the kernels have symmetries, and locality, meaning that the field of view of a neuron is actually quite limited because gravitational physics only really affects the structures locally, and galaxy formation physics is relatively local compared to cosmological scales. And it turns out that way we can write down a neural network that only has 17 parameters, which is laughably small for neural networks. Typically, the big models that you hear about have billions of parameters now. We can include it in this forward model, this Borg framework, to map dark matter density to halos and leave the parameters of the network just as additional parameters in our Markov chain. So this is quite interesting, because doing that, we don't train the network on simulations. We just say, okay, here's a neural network that provides some flexibility for the modeling, and we just learn this modeling. We learn the link between dark matter and galaxies from the data themselves. So there's no training data. We just run this thing on one set of data and vary the parameters of the network at the same time as we vary the initial conditions and everything else. And then so we proposed this in 2019. And in 2020, about a year later, there was another paper that had a similar approach, but using Lagrangian, a model predicting particle displacements. So here we're dealing with the density field, galaxy density field. So here's a movie of that running. So again, Borg is running in the background. Here's the initial condition at first, so not much. Here are the simulated data. This is a simulation, so simulate data, where we just take we have halos of all kinds of different masses drawn from the underlying dark matter distribution. And then we have Borg basically trying to predict the halo distribution by first solving for the dark matter dynamics, and then having this neural model for the halo mass function as a function of the local density, and not just the local density, but the entire dark matter distribution gets converted into a halo mass function in every pixel. And you see that it does learn these halo mass functions. You can see how they vary, and it does learn the initial conditions. You see the filamentary structure here. So this is actually not the initial conditions. Those are the ones that are being learned. What I'm showing you is the forward evolved redshift 0 dark matter distribution. And so at the end, the predicted halo distribution by the neural network actually matches very well the actual halo distribution. And because we have a physics model, the initial conditions have been reconstructed. Okay. So this is one example how to use machine learning in the context of a physical model. But let me go much further now and go beyond an explicit likelihood model. Okay, so going back to how to do cosmology, or well, actually more generally, how to do science a Bayesian way. Remember, we write down this likelihood, we take data, that gives us this part, we pick a prior, that allows us to write down a posterior distribution for the parameters we're interested in. It could be the initial density distribution, could be cosmology, whatever is in those parameters. Actually, also galaxy formation parameters, all the things that are relevant. But the problem is, what if the data are so complicated that we don't know how to write down the likelihood? So can we do this without this likelihood function? So the full problem, therefore, we need a lot more freedom than we can have in an explicit likelihood approach. So we want to have the freedom to make our physical model anything we want. We want to have the freedom to project, summarize, cut, mask our data in any way we want, so that we address this issue that the model is always imperfect. Even our best physical models are somewhat imperfect, but we want to treat the data in such a way that the treated data can be modeled well. And we recognize that simulating data is often much easier than deriving an accurate likelihood. It's not necessarily easy, but it's easier. So we can write down a simulation code, at least, that does all kinds of interesting things with galaxy formation and so forth. How to write down a likelihood form that actually is adequate for that, in many cases would be very hard to see. So the question then is, can we analyze data if all we can do is simulate it? And this gets us to likelihood-free or simulation-based inference. This is the class of techniques for building inference engines when the explicit likelihood form is unknown or intractable, but you can simulate it somehow. I like to call this, so there are two names for it: likelihood-free, which is misleading because there still is a likelihood, it's just that you don't know how to write it down in closed form. Simulation-based means that computer simulations are used to draw from the likelihood. I like implicit likelihood inference better because it is more general. Doesn't necessarily, because you could even imagine this in contexts where you don't necessarily have computer simulations, but you could even have human intervention that you could include in this, where the likelihood implicitly includes some decisions that are made by humans as they analyze the data. Okay, so this has been used in cosmology now for some time, in weak lensing in particular, or image analysis. And the first papers, I'm sure the authors of the first papers are listed there. But this has been limited for the following reasons. I'll show you why this has been limited until very recently. Here's how this works. Okay, so here's Bayes' theorem again. We don't have this likelihood, but if we can simulate the data with all of its complexities, all of the realities of actual data, then these simulations are actually draws from the likelihood. Okay, the likelihood is the probability distribution for data given some model. So simulations are draws from this likelihood probability density function. This is maybe slightly confusing because you like to think of the likelihood as a function of the parameters often, but really the likelihood is probability distribution for the data given a set of parameters. So it's forward simulations of the, and then when you stick it into this formula and you evaluate the posterior for fixed data as a function of the parameters, then you happen to have this functional form here on the right, and you fix the data and you vary the parameters, but that's because you're dealing with the posterior now. Okay, but the meaning of the likelihood is the predictive distribution for the data given some set of parameters. Okay, so how can we use that in inference? Let's say we have a bunch of parameters, 5 parameters. We draw those from a prior distribution. We have to pick that somehow, so we draw from that. We simulate the data. Okay, here's our simulated data. And then we look at it, we test whether the simulated data is exactly equal to the data that we have taken. With all of the error bar, not the error bars, it's just the actual raw data that we've taken. And if they are the same, or at least the same up to some epsilon that's defined in sort of some similarity function or distance function, then we accept the set of parameters we used to draw the data. If not, then we throw those parameters away and try again. New parameters from the prior, simulate forward, look at the simulated data. If they're exactly the same as the real data that we have gotten, we accept the parameters. And so in the limit where this epsilon goes to 0, so in the limit where we only accept simulated data when they are exactly equal to the true data, in that limit, these accepted samples from the prior that satisfy this criterion are samples from the posterior. Okay, so in principle, this is an in principle way. This is not how we actually do anything, because this was actually how people did it in the early days in the papers I just mentioned, with data sets that were often extremely limited with a very, very small number of elements, because as you can imagine, when you have a million data numbers in your data set and you're forward simulating a million numbers, they're never going to be exactly equal to each other, right? So you never get acceptance. So typically what had to happen was you had to choose a very, very large epsilon. So to be very permissive that you accepted data, even simulated data, even when it wasn't really a good match to the true data, to get anything at all. So then you typically you still get good posteriors, but they're just very wide and not very informative. They're not wrong, but just it's a very lossy thing then. So the problem, therefore, is to reduce the dimension of the data massively. This is a problem that we started looking at in 2017. And it turns out, so with these techniques here, score compression in 2017, there was earlier work in 2000 that for some specific cases does the same thing, but this is the most general form here described in this paper. You take your n parameters, you simulate some data, you then extract however many summary statistics from this data that you want, and then turns out you can always compress it down to just n numbers, where n is the number of parameters. So you have n summaries, where n is equal to the number of parameters. You can always do that without losing information about the parameters. So this is in terms of Fisher information. So it's information optimal. Okay, so here's a scheme where you do that. You have some summaries. You compress your data into some summaries. Of course, how to choose the summary is a different question. But let's say even if you could compress into a very, very large set of numbers, as permissive as you want, if you have, if you can do the score compression, then you can always get the numbers down to just n parameter summaries. And then you can compare those in a way similar to what I was showing you there before. If you have 10 parameters, you're just comparing data in a 10-dimensional space. And that gives you samples from your posterior distribution. Now, again, just doing this accept reject can be extremely wasteful because you're throwing away a lot of the simulations, and the simulations could be very expensive. So it turns out that here, this comparison of the simulations and the data, which, by the way, as you can see, the data goes through exactly the same pipeline as the simulations, get compressed the same way. So this is very important because this means that whatever you do in the compression will never bias you. If it's not optimal, you might get slightly suboptimal error bars, but it's never going to do anything bad to you. I mean, you're never going to be overconfident. But how do you then compare this? And can we go beyond this weird accept reject thing where we throw away most of our simulations? So in density estimation likelihood free inference, or Delphi, people in the statistics world, the machine learning world, were thinking about this at a similar time to us. So we wrote a paper about this in very early 2018, where we used normalizing flows to represent the density distribution. And the idea is that we can use these simulations to learn the likelihood, and the posterior, actually, both, depending on exactly how we do it, from these forward simulations. So instead of just doing accept reject, we actually also learn the likelihood in some part of the parameter space that is, and some part of the data space that's not exactly equal to the data, because often things are smooth, and that makes things a lot more efficient. So here's an example for the case where we can do explicit likelihood and this implicit likelihood Delphi form, the density estimation likelihood for inference. And we find that we get exactly the same results. And it turns out that actually this is even faster. This is for a 5-parameter problem, 6-parameter problem. We can do this even faster than we could do this with the explicit likelihood inference with Markov chain Monte Carlo, because it turns out for our problem, the simulations are all parallel, whereas in Markov chain Monte Carlo, of course, you have the sequential search. So the Markov chain Monte Carlo here had hundreds of thousands of samples, but the likelihood free inference was done with only a couple of thousand simulations. All right, so but what happens when the number of parameters gets large? You still have then a large number of these summaries. Often you have kind of not that interesting parameters, but you still need to keep them in the problem. These are called nuisance parameters. And it turns out you can actually write down the compression in such a way that you only ever compress to a set of numbers that's equal to the number of interesting parameters you have. And that's described in this paper. So we call this nuisance hardened compression. And this likelihood for inference framework and getting the posterior out, the joint posterior over all the parameters, is described in this paper here. And there's a package that you can use to download. Okay, but remember we always said that we didn't want to use the likelihood, but then at some point I slipped it in there that we were using score compression. And if you know your statistics, you realize the score is actually the derivative of the likelihood. So the optimal compression actually depends on knowing the likelihood. So we were not using the likelihood to build the posterior, but we're using an approximate likelihood to build nearly optimal compression. Now that doesn't bias anything. If the compression isn't optimal, you just lose a bit of information. So it's better in that sense. But still we somehow need the likelihood here to do the compression. These are paper references for how to do optimal compression when you have the likelihood. But again, we're in a regime where the likelihood is unknown or intractable. So can we go beyond that? And again, we can use machine learning. So it turns out we can write down a training scheme and neural networks that will compute the score function, so the derivative of the log likelihood, even when you don't know what the likelihood is. So, and those are maximally informative summaries that maximize the Fisher information. Okay, this is described in this paper here. So it's very nice because, I mean, Fisher information is very widely used concept in particle physics, astrophysics, and so forth. And it turns out you can train neural networks to come up with summaries from the entire data set, including all of the raw data, that will compress it down to a set of summaries that are of lengths, that have the same numbers as the number of parameters that you have. And it turns out actually that the compression is the score function. So these are field-based implicit likelihood inferences with these information maximizing neural networks. So here's how this works. You stick in a distribution, like a field, a galaxy field, for example. And the examples I'm showing here, we're using approximate models for the dark matter distribution, or log normal models for the galaxy distribution. Correlated log normal. So you then pass it through a neural network. It produces a number of summaries. It's equal to the number of parameters that you have. You compute the covariance of these summaries and how they change when you change the parameters. Use that to compute the Fisher information, and then you backpropagate, because you take the log det of the Fisher information. You backpropagate to optimize the weights of the network, so the network finds optimal summaries, most informative summaries. So here's how this works for Gaussian field, just to make sure that we do optimally in case where we know what the answer is, and yes, it works. So if you know about Fisher information, you always have to pick a Fiducial model where you evaluate the Fisher information, and we find it's very robust to the choice of Fiducial model. The other thing you can do, of course, is iterate the Fiducial model. So you do this once, you train the network at these parameters values here. The dots, by the way, are what we get for the posterior samples from this method, and the orange contours would be the exact likelihood. So it works extremely well. But if you're Fiducial, you can then update the Fiducial model to see whether you can further optimize the compression. But again, the compression itself is never going to bias your analysis. We know in this case what the theoretical information bound is, and as the network trains, we can see the summaries approaching that information bound. That's very fast for this problem. These are now non-Gaussian fields, so these are log normal fields with cosmological statistics in terms of two-point correlations. And we can extract cosmological parameters. And there's 4 different fields, and we find these contours which match extremely well, what we expect. And so the truth is where the dotted lines are, and this is an optimal analysis, posterior analysis from non-Gaussian data. So if you want to play with this, there's actually a tutorial here on Google Colab that where you can go through this whole analysis. All right, so these kinds of likelihood-free inference techniques can also be used with other summaries, of course. Doesn't have to be score compression, that's optimal, but you can also use networks that have been trained to guess back the parameters and use those parameter guesses as the summaries. And so we did this with light cones of 21 centimeter data. So these are a couple of different models. So here's this is the brightness temperature contrast for a piece of light cone from 21 centimeter simulations. We have all of these simulations, we train to guess back the parameters, and then we build this posterior surface, posterior distribution using Delphi in this paper. And you see that it works very well, and it turns out that a power spectrum based model gives you the wrong statistics. So it's interesting that if you're taking the power spectrum, you're putting a Gaussian likelihood on top of a power spectrum, you don't seem to be able to get the right statistics out. Okay, so this still seems somewhat complex. We now have a scheme for doing optimal inference, get the full joint posterior for anything that we can simulate. But there's this compression step, and then there's the learning step. Can we go, is there some way where we can just go from the data straight to the answer, straight to the posterior contours? So yes, but then you lose this robustness where, whatever you do, you basically just screw up the error bars. I mean, the size, you get wider error bars than you would. Here now we start trusting the deep learning more, okay? And this is called moment networks. This is what, so by the way, the IMNN stuff, the information maximizing neural network stuff is what Lucas will talk about in a few weeks from now at Minerva. And then these moment networks is something that Niall Jeffrey and I developed. So the idea here is that we train the network not just to learn the some guess, okay, but we actually train them to learn. We set up the training in such a way and the losses in such a way that the neural network returns to us posterior moments. So, for example, the posterior mean and the posterior variance. Or we could even train it so that the network returns to us the posterior distribution for the low dimensional marginals, which is all we ever look at typically in any case. So even with 1 million parameters, now we can just look at the marginal means and variances, or even the marginal posteriors for those parameters in separately without having to explore the full joint distribution in this extremely high dimensional space. And we can sort of do this shortcut. I'm going to skip over this. This is an example in the paper that's highlighted here for gravitational wave inference, so not a cosmological example. Here's a cosmic microwave background foreground cleaning example with here now we have 10 to the 5 parameters, all the pixels here, and basically you start with foreground obscure data and you get the mean and variance at every point, and you see the variance actually depends on the input data, which just because the model is very non-Gaussian. It would not do that for a Gaussian model. Here's the same thing applied to cosmic microwave background polarization data. And this is includes another interesting technique, because here we're actually training our network using only one single simulation of the foregrounds, the cosmic microwave background polarized dust foregrounds. And we're able to do that because from that one simulation, we can generate many, many realizations that have the same morphology using a technique called wavelet phase harmonics, which quantify in detail the morphology of the simulation outputs. So we just with a single simulation, we can train this network to de-noise or foreground clean polarization data. So you see, here's the truth, here's the data, and the scale is different because the foregrounds are so large that you don't even see the underlying structure or much of it anymore. Here's a little bit in the cleanest regions. And then it does the reconstruction, and you can see in the highest, most foreground dominated regimes, you get a little bit less amplitude in the reconstruction. In the clean regions, you get large amplitude. Here's the marginal variance per pixel. And this has been done, just with, and this network is now trained, and you can stick in data and it will immediately give you the answer. So it's, there's a lot of amortization happening in the training. We can check that the posterior statistics are good, and they are. So the returned means and variances of all the pixels are very accurate. So that's in the paper. Oh, it's actually now published. So this, I should have updated that. Okay. A note on uncertainty quantification. So I'm sure you've heard a lot about Bayesian neural networks. They do give you some level of uncertainties in your neural network outputs, but very far from actually giving you good posterior approximations. The stuff I'm talking about is designed to return to you the posterior. This basically comes up with a stochastic model, which is for the network weights, which is not really principled. So here is an example of, I'm not going to go into the details, I just wanted to highlight this as a paper that came out recently with collaborators at Montreal, where we actually do a detailed test of how well the posteriors represent the truth. And when you do Delphi, okay, which produces in this case, the posterior is represented in terms of a mixture density network. We have that as a possibility. You can also choose normalizing flow. It turns out it gives you basically perfect posterior properties, the posterior quantiles. Whereas if you do these Bayesian neural networks, even when they're quite highly tuned, they typically don't approach that. And so you have to somehow calibrate them, externally somehow to make sure that they work well. So it's this is a potential. So be aware when something called Bayesian neural networks isn't necessarily really, I mean, it's Bayesian, but not necessarily for the right model. Okay, and now in the last couple of minutes, if I still have a bit of time, I wanted to show you what happens when you take all these methods and you apply them to detailed cosmological simulations with hydro simulations. So this is in the context of the CAMELS collaboration, cosmology and astrophysics with machine learning, where we have two separate sets of hydrocodes that produce galaxies and all the rest of it from a set of initial conditions. Cosmic Web, which we've made publicly available. So this is led by Paco Biascuza Navarro and Shai Guinel, Danis Angles Alcazar at the Flatiron and Columbia and Berkeley. Here are examples that we get from all kinds of observables. So this produces 13 different fields for all kinds of different cosmological parameters and simulation parameters, for different feedback parameters. And you can look at these data sets. Here's the website, and use that to train your own machine learning algorithms or do astrophysics with them. So here the idea was, can we learn cosmology from these various outputs? Can we learn cosmology from, for example, the stellar mass, or from things that are closer to observables rather than the dark matter, which is not directly observable, except through lensing potentially. So, but even with lensing, you have baryonic effects that affect the dark matter distribution. So we have these machine learning trained to get cosmological parameters and the simulation parameters from these all of these different fields. And notice that this goes down to very small scales. I told you before with Borg, we were looking at maybe 3 megaparsec, and this is 30 times smaller in scale, these simulations. And it turns out that, yes, indeed, we can get cosmological parameters. This is matter density, and sigma 8 is a measure of the fluctuation size from these simulations. This is the fluctuations in the dark matter. So this is a parameter for the primordial amount of fluctuation, really, indirectly, non-linearly related to that for these very small scales. And you can see, so these are using moment networks. So this is the loss you would get from a moment network that I described before, that with Niall Jeffrey. We'll give a talk in a few weeks from now. And you can see that we get very consistent estimates with the truth, and then also these hydroparameters. And this is from the gas temperature. So this is something that's in principle observable with, for example, Sunyaev-Sedovich or X-ray measurements. This is the gas metallicity. So something quite far removed from the dark matter density, and still we can get a lot of information about cosmology from that. So this is what we've learned from this. It's interesting because, you know, this is not real data analysis. We're still working with simulations, but we can already draw some conclusions from this. First of all, there is cosmological information on very small scales. Clearly, when we don't go down to 100 kiloparsec, we cut it off at a larger scale, we lose information about cosmology. So it's very interesting. It says that in spite of all the hydrodynamic processing, there's still information that persists on very small scales. It turns out that the hydro outputs actually contain more information than dark matter density. So this is counterintuitive. People always thought, well, if you could just get a nice map of the dark matter, then everything would be, we'd get everything we could possibly get. No, at a given redshift, in fact, if you combine all the information from all the different hydrodynamic quantities, you actually end up with more information than if you're shown the pure pristine dark matter. And it turns out, because we have multiple hydrocodes, different baryonic physics implementations, if you're looking at the total matter, then you can train on one hydrocode and still predict the correct or infer the correct cosmological parameters from simulations from another hydrocode. So this is good news for weak lensing at some level, because weak lensing probes the total matter, and the baryonic physics effects on the total matter don't seem to be somewhat robust, at least to these different code implementations. So here is I mean, that's just a plot that shows that. I showed you the conclusion first. And lest you think that this is because baryonic physics is so similar in these two different codes. No, actually, this is the gas temperature, and you see it looks very different in this slice for the SIMBA and the electricity TNG codes. So this is these results are not really trivial. Okay. So now, one of the things that we need for this is very large numbers of simulations still. I mean, we're talking about thousands and thousands of simulations. So one project that I've been doing with my student, Nicolas Chartier, who's graduating this year, has been to see if we can build likelihood approximations while reducing the number of costly simulations. And the idea was, well, if we have some fast way of predicting approximately predicting what things look like, can we somehow use that together with a few full simulations to get the best of both worlds: the speed of the fast surrogates and no bias compared to the full simulations. And it turns, here's an example with the power spectrum from a full n-body simulation compared to a fast approximation called COLA that uses Lagrangian perturbation theory to reduce the number of time steps by a large factor. So it's about 100 times faster or more than a full n-body simulation. And turns out that compared to 500 full n-body simulations, we can basically get smaller or similar error bars depending on the regime with just 5 full n-body simulations and a whole bunch of these surrogates using these statistical techniques. So I invite you to look at this paper if you want to learn more about this. one of the big problems for upcoming surveys is how to estimate covariance matrices, because that typically requires many, many simulations. This is not just true for large-scale structure like Euclid or DESI, etc., SST, but also for the cosmic microwave background. And in fact, we're working with SPT and we find also there that we get similar reductions so this paper here looks at a 10-fold reduction with but it turns out there's an work coming up in a matter of days. We'll be on the archive in a matter of days, where we show that we can get 100-fold reduction in the number of simulations to get comparable accuracy, for example, on parameter contours from likelihoods constructed with these covariance matrices, compared to what people thought that was necessary. So going down from 10,000 simulations to just 100 can be the difference between completely infeasible and regularly possible. So this opens up new interesting things, like, for example, you can, if you already have a whole bunch of simulations for one model and you want to change your theory, but you can still run the same initial conditions so that the outcome is correlated, you can use this technique to use the full simulations that you already have as the fast surrogates for the updated new theory that you're about to run, and just run a few more simulations and basically transport all of the results from models you've already run to new set of models. Okay, so here's the final set of thoughts. The summary is machine learning will help us solve cosmological problems that are still intractable today. We should think about AI safety. I've mentioned that in a few places. This whole carpool story, this method for reducing the number of simulations is actually also has that in mind. I can talk more about that if you like, because a lot of the times, because of the heavy simulation cost, collaborations use approximate methods to construct their likelihoods, and then there's a potential of bias that comes from that. And another way of looking at this idea is that you can use these approximate methods and then just run a few extra simulations to completely eliminate any bias in these approximations. Well, there's just a general comment at the end here that wavelets, Gaussian processes, fast endpoint function estimators, tree-based methods, and so forth are also machine learning, and deep learning, which is what I talked about most here, except for this carpool stuff, which is actually classical statistical method at some level. I mean, we should not close ourselves off to all of these powerful other statistical techniques and machine learning techniques. We should just use whatever is possible, whatever makes progress possible. So thanks very much, and I'm happy to take your questions. Here, by the way, is the slide with a bunch of codes if you want to play with any of this. And simulations, if you want to download. All of the simulations I mentioned are completely free and downloadable. Some of those data sets are the largest data sets ever been released in cosmology.
Thank you for this super rich talk with a number of references I think we have to look at to get more details about the different projects. I don't know if we have some questions. Some people had to leave during the talk. But for people who are still there.
Is anybody still there? Okay, so we still have a few people.
David said that he would ask you a question by email.
Okay.
I have just a small naive question. When you presented the compression and the summaries, can you learn anything about, I mean, what are those summaries exactly? I mean, do you have an idea of what they are? and what does they tell you about the important information compared to the parameters you can get at the end?
So it turns out, so in this information maximizing neural network, we kind of realized after the fact that what we built was a tool that computes the Fisher score function when you don't have the likelihood. So they're really well, affine transformations of, because you know, linear. As long as you have a linear transformation, it doesn't matter. You can always undo it if it's full rank. But it's going to give you some linear transformation of the score function. The score function is the derivative of the log likelihood. So it's kind of this interesting thing where you can use a machine learning technique, these information maximizing neural networks, together with their particular loss function, to compute the log derivative of your the likelihood of the log, the derivative of the log likelihood, which is the Fisher score, without knowing what the likelihood is. It's kind of it's just because essentially you can write down the problem of computing that thing as an optimization problem, and that's exactly the optimization problem that these codes, the neural network training, solves. So that's the trick, basically, and I think that's a useful way to think about deep learning in many cases. If you, I mean, I like I like knowing what I'm trying to compute, and in deep learning sometimes you know, it's not exactly clear what it is that these things are computing, and at least when I write down a loss function, I like to know what it ought to compute, even if maybe the deep learning, the network needs to be expressive enough, training needs to work. So there are some conditions, but I'd like to know at least what the thing is trying to compute, so that I know how to interpret it. And that's very, very clear in these contexts. So it's we know exactly what the thing is trying to compute. So it's actually, I mean, there's another story there if you want to hear it, because, I mean, yeah, if there are other questions, maybe ask.
No, go ahead.
Well, so initially when I thought about this information maximizing neural networks, we had to, in order to compute the Fisher information of the network outputs, again, we had to make some kind of a likelihood assumption for the distribution of these outputs. And initially I thought, well, they're supposed to concentrate information, and so asymptotically they will probably be close to Gaussian. So let's just write down the Gaussian likelihood and use that Gaussian form to compute the Fisher information of these outputs, and then we'll see what happens. That was basically how this got started. And then it was working so well, and even when the inputs were very non-Gaussian, approximating the output statistics of the network as Gaussian to compute the Fisher information seemed to work extremely well and always produce the right Fisher information in all the cases where we could compute it, even in non-Gaussian cases. So this got me, and some people would, when I talked about this, some people would say, well, but you're just replacing one likelihood approximation with another, so who knows, how do you know that this will always work? It turns out, so this is work that's happened afterwards. It turns out that the Gaussian, the fact that we use the Gaussian form for the Fisher matrix for the network outputs actually will give you the correct Fisher information in all cases, regardless of the input, the statistics of the input data. So this can be proven. And that's quite a powerful, maybe surprising result. So this is why I could say with confidence, when you're asked the question, what is it that these things actually compute? Well, it turns out they compute the score function of the underlying likelihood that we don't know of the full data set, even though we're using a Gaussian form for the Fisher to compute the Fisher information. And that seems to be a general result.
Okay, so I think we can stop now, probably. And thank you again.
It was a pleasure.
And,
yes, thank you. Very interesting.
Thank you. I look forward to your emailed questions.
And see you next week for the next seminar. Thank you very much.
All right. Bye. Thanks for the invitation.